컴포말 다이어그램 같은 거 만들 때
네.
이걸 일부러 컴팩트하게 만들어가지고
네.
바운더리 있게 만들잖아요.
네네.
이걸 그냥 컴포말 바운더리로.
아, 오케이. 근데 그게 필드 티어리에 등장하는 컨포멀 바운더리 또는 컨포멀 바운더리 컨디션이랑 같은 거예요? 아니면 그건 다른 건가?
거기까지 모르겠어요.
Okay. Ready? Okay. Let's move just a little bit. Okay, cool. All right, let's get started. Any questions? I think there was no question, so let's get started. All right, so last time we started discussing vector field. Right, and then we said, we talked about the fact that it's a vector field, and then we recall that vector representation, which is real, and therefore simultaneously also pair invariant was this, right? So we talked about that. Okay. So then, if we focus on transformation on the rotation only, then we recall that this is basically two independent SU2 representation. So this can be factorized into dimension 3 representation and then dimension 0. So there's a scalar and then there's a vector, like vector not as a Lorentz but as a rotation, 3-dimensional rotation. Okay. What that means was that given a vector field, as we talked about, we can decompose 4-component vector field into a transverse part and then say scalar part. So this satisfies a condition that it is actually transverse to the momentum direction. Or if you want to express this as in momentum space, this just means that in a product of this to a momentum of propagation is orthogonal to each other, right? So this was the case. And then the way we start building up the theory of vector field was by saying, okay, let's start writing down the most general action, right? And then we listed a couple of possible contractions, and the first kind was this. Okay, let me be consistent. Okay, mu, good, so that's allowed. And then the second thing was, let's see, mu, nu. So that was the second term. And then the last term you wrote down was C, A mu, A mu. Good. Okay, so that's what we talked about. And then I made a comment about these two terms first, since there seems to be a little bit of confusion, so let me clarify it again. So between these two terms, which has two derivatives, if we only included this term, for instance, and then you don't actually tell me that you had in mind that by A mu, you had in mind this representation, then you will be in the phase of confusion by saying, oh, from this can be either I view this as a totally unrelated index as a space-time index. So now this you can view as just some scalar field where you have an index, which is nu, but I'm just rewriting as I, which has a 4 different components. And so in other words, if this is the only information you have as a Lagrangian, you would not know whether you really mean, I really mean by this expression for Lorentz index or just internal field space index. So if you interpret this way, you simply have a 4 independent scalar field, right? And then you're just writing down a kinetic term for a 4 independent scalar field in a compact notation. So therefore, without this term, you could say that, oh, am I actually talking about 4 independent scalar fields? So that was this. Simultaneously, you might say, oh, this might be actually Lorentz index. Then you can say, oh yeah, then I must be talking about these two. So the point here is that if I set b equal to 0, then this term alone, also including this term, right, can mean either this or that. So you don't know which one we are talking about. And in fact, even theory will say, I don't know which one we're talking about. But as long as I add a second term, then in order for this to be Lorentz invariant, you don't have an option but saying that this mu appearing in the field must be not an internal field space index, but this must be space-time index. So at this point, you know that we must be talking about this second case. Okay, so at least. And then what I said last time was that there is a unitarity. And then I said unitarity implies that A plus B must be equal to 0. Okay, so that's what I said. So to start out this discussion, so this is non-perturbative input. And as I said, good. So let's talk about that. So statement was, if I have a quantum field theory, so let's start off by saying, so let's suppose I had a time order 2-point function of some field. And by this, I don't really mean scalar. I just mean arbitrary quantum field. Okay, and then this can be rewritten as follows. So this is integral over all possible mass parameter. And then one can show that non-perturbatively, even without using techniques of quantum field theory, just by using Lorentz invariance and stuff like that, Lorentz invariance and representation, you can show that 2-point function always takes this form. Okay, so this is called spectral representation. We may discuss that at some point. Spectral representation.
Professor,
Yes.
is it
Rho.
X?
X.
X and U scale.
Sorry. Rho. Okay. So let me give you a mini explanation of this expression, first of all. So what does that mean? So for fixed mu, so you just look at the fixed mu, this looks like it's a single propagator, right? This looks like single scalar propagator with the mass mu square. And then mu, which is called the spectral density, tells you what is the probability for that particular mode to be excited, okay, or is there. And then the expression is I'm gonna sum over entire mass parameter space. So basically, given a mu space, and then here is a rho. Suppose this rho, spectral density, is non-zero for only particular value, m squared, and then this is like picked and then 0 everywhere. Okay, so then, for instance, in other words, what I'm saying is that the particular example where rho is actually proportional to mu squared minus a given value m squared. Then you see that if you look at this, oh, I forgot this, I must be talking about Fourier transform. Sorry. So this is space-time, and then suppose I look at the Fourier transform of that. In other words, if I do, I want to transform back. So 4x e to the minus e x minus y. Okay, so now I don't have to. So okay, so starting out with the position space propagator, let me Fourier transform back to the momentum space. I'm saying I get this expression. So one particular example of a spectral density, which is like delta function picking at a specific value, you see that you're going back to a single scalar particle, right? But what I'm saying is, in general, in quantum field theory, if you have an operator, it doesn't need to be even fundamental field operator. It can be some composite operator. It's okay. And then if you look at a 2-point function, it takes this generic form, and therefore this now mu rho mu, which is once again called the spectral density, maybe can take some arbitrary shape, which means that this particular operator, when you act on the vacuum, can create a lot of different kind of excitations, right? As you scan over the mass space. And another important example is that appears often in particle physics, suppose, is, for instance, if you had a free particle, so you start out with a single mass, okay? So there's a delta function peak there, so you know there's a single propagating mode, but then you found that starting from some cutoff, suppose 2m squared, it has some continuum distribution. So for instance, this will give you a lot of information about the quantum field theory. So there is an excitation called one particle pole, and then starting from some mass threshold, all of a sudden some continuum distribution is possible. Okay, and this later we'll discuss is capturing what is known as a decay process of a given particle. Anyway, we'll get to that. So coming back to here, what I said last time. So this is not to discuss this part. The last time, the statement that I made was that if we go to the Euclidean space, so starting out with the Lorentzian square, I went into the Euclidean momentum by making weak rotation, meaning I just exchange this with that. then one can show that this momentum space propagator. So this is the momentum space propagator as a function of a Euclidean momentum now. As the momentum goes to infinity, should be equal to greater than some particular positive number. It doesn't matter which number actually. So let me just write it C. And important thing is this is positive number. Okay. So that means the way you should read this equation is that momentum space propagator as the momentum goes to infinity cannot die faster than 1/p². Okay. So that's the lesson that you have to extract from this. So there's a non-perturbative input that any unitary QFT two-point function cannot decrease in the large momentum limit faster than 1/p². P². So, okay, so that's the key information. So using that, we can now show that it should be A plus B should be equal to 0. Okay, that's the part. I don't think I showed last time, so let me show that. Okay, starting from this.
반전 녹화되고 있는데 괜찮은가요?
Sorry.
film 끝나서 죄송한데 이거 저우 반전돼서 녹화가 되고 있는 것 같은데.
페이지에 다 만든다고.
네.
결정을 안 했는데. 계속 이대로 녹화하시죠. 녹화하고 영상을 뒤집습니다.
What happened? Oh.
You are left-handed.
Very good. I'm actually, yes, half left-handed actually.
Okay.
So I'm actually both-handed. But you know how to flip the thing?
네, 뭐 어떻게 하면 되겠죠, 사실. 그 영상.
Okay.
오케이, 굿.
Okay. I didn't know we had a special setup so far. Anyway, let's move on.
많은 소리 올렸어야 했는데요. 많은 소리 올렸으면 좋았을 텐데.
Wait, are we joking or no? No? Yes? Okay. Okay. Really? No, anyway, let's okay. So let's show what's wrong with that. So let's start out with this Lagrangian, which I just erased. This is like cannot copy paste. I have to rewrite. But let me do the integration by part. So if you remember, if you do the integration by part, you get something like this. This. And then a mu. This. And then B here. And then C. A mu. A mu. Good. And then we decompose this into transverse and then this scalar part. Okay, last time I said that longitudinal, and that's what is said in Coleman too. But today, let me distinguish transverse and just scalar. Let me just keep saying that, okay? Because later on, within the transverse part, we have to talk about longitudinal polarization. So I don't want to be confused. So I'm gonna stick to either vector scalar or transverse scalar, okay? So that's what I mean. So let's plug it in. If you plug it in, this, first of all, let's just keep this part. So what do you get? So A transverse mu, B transverse this. Okay, but then B part is simply 0, right? Because if you have a transverse, by definition, this is 0. Okay, so B term drops out, and here you get plus C transverse mu. So that looks like really like 3 mode, because I projected at one of the thing, having a propagator with the mass. What about this piece? Let's work that out. So with this, I will have a del phi, del pi. But let me do the integration by part one more time. So I pick up the plus sign, and then back to the 4 square. That's what I mean. Pi. So are you with me? Okay. Here too. So I'm gonna plug in del by default, and then I'm gonna do the integration by part again. So that will give me therefore A plus B. All right. And then from that piece, if I do the integration by part, I get minus C pi box pi. Good. Good. So in order to get this constraint, we're going to focus on this scalar degree of freedom. Because if you look at the scalar degree of freedom, the Lagrangian is a higher derivative, meaning it has a more than 2 derivative. Remember, box is a 2 derivative, so this has a 4 derivative. Okay, so let me just focus on this pi Lagrangian.
Sorry. Where's the mixed term?
Where's the mixed term?
Principles part times from
But then you see, if you have a mixed term, you can always integration by part and then acting on here, and then you just annihilate this term. Good. Okay. So let me look at this term. So then if I actually look at this in the momentum space, this will look like a plus b, oops, a plus b pi e to the 4. Okay, let me write this way. Pi e to the 4. Okay, that looks okay. Let me rewrite. So pi a plus b e to the 4. And then this will give me extra minus sign. So c times p squared times p. Okay. And then the propagator, so let me write it as a pi sub pi to maximally confuse you, will be inverse of this. Okay. So that will be c. Actually, you know what? For real scalar, usually you have a 1/2, derivative pi squared and so on. So let me just rewrite it as 2 times 2. But that doesn't matter. Okay, half really doesn't matter. So inverse of that thing is this, the 2a plus b, b4, 1. Okay. Good. So this we can rewrite as eventually I'm gonna pick c to be negative sign, but that's detail, as now p squared minus you can work it out, plus minus c, a plus c. So let's check. So now if I just complete this, what do I get? A plus b p squared, and then c plus p squared. I factored out this. And then that minus that, I have t1. Okay, so this must be right answer, I think. Up to minus. So what's the lesson here? Okay, the lesson is the following. So this Lagrange, which looked totally, a healthy, nice thing, but secretly, if I included this scalar degree freedom, it had a higher derivative action. In particular, if you look at the propagator, and propagator is like a 2-point function, right? So starting at the vacuum, you produce guy, propagate, and coming back. So it's like inner product of the same state. Since I'm talking about the real field. Okay, so if I look at this, if this is a real field, this is a norm of a phi acting on the vacuum sort of thing. So in particular, if you look at this, there's always a relative minus sign, so long as I pick a general a plus b. And then, in other words, this always has, if you like, in a negative norm state. You see, you might say, oh, can I pick this a negative sign here? No. If you take a large momentum limit, then anyway, cancel, it behaves like 1 over p squared with overall minus sign always, right? Regardless of what sign of a plus b pick. Is that clear? So in a large momentum limit, this behaves like always 1 over p squared, when this behaves like a 1 over p squared. Okay? So 1 over p squared versus minus 1 over p squared. You always have a negative norm state. In other words, you have a ghost. One kind of ghost. Hence, this theory is ill-defined in a large momentum limit. And how do you kill that? Well, I have to get rid of the higher derivative term. How do you do that? Well, you have to set this term to be 0. Because this was the culprit. This was the p to the first term. Therefore, in order to be consistent with a unitary, I know that I have to set this to be the case. Okay, so that's the argument. Okay, so with that established, now let's move on. So then with that, Lagrange now, I can write it as, in the original form, there's a rho minus sign A, and then, what did I say? Mu, okay, mu minus nu. Okay, so that was the one piece, and then we had a c, a mu, a mu. So now I just inverse that term. Okay. Good. So let's build a little bit more intuition about this. But before I do that, you can check that this part of the equation can be rewritten as auto sign. I will introduce. So far it's totally notation. So far this is totally notation, and let me check the sign. I don't want to give expression that has wrong sign everywhere. Let me just make sure I give you the right sign. There's a half. Okay, good. So what is F mu nu? F mu nu is defined to be derivative. This is got an anti-symmetrized between the mu and mu. So this is called the field strength. Now, so far, what I'm saying is that this is absolutely just an invention of a notation, nothing else for now. Okay, but we will explore a lot about this meaning soon, and you can check that this is a rewriting of the expression. Okay, good. And now let's actually look at the equations of motion of this thing and then understand slightly more about this aspect, meaning there's a scalar versus a vector mode. So let's look at the equations of motion. So to do that, let's see, so the equations of motion of this thing, you can derive. And if you do so, let's see, you get, you take a derivative with respect to derivative of this guy, which is a mu, a nu, and then you have to take a derivative, but there's vectors of 2, so minus 2a. That's the first term. And then the second term will give you, okay. To build an intuition, let me actually analyze the equations of motion of this guy, meaning let me say A times that and then B times that guy. So for now, let me not assume B is minus A, which already reinforced because we knew it. But for now, let me pretend I don't know that. So therefore, I have a nu. Oh, I wanted to have independent nu index. Nu, okay, so that's that term. And finally, I will have a plus a 2c a nu equal to 0. So this is the equation of motion. Okay, so there's a minus sign for the derivative term, and then no sign for the polynomial term, as usual. Okay, so to understand the meaning of the equations of motion, let's actually try plane wave profile. By which I mean I'm gonna try this is some factor, prefactor, and then for now, let me just look at the positive frequency solution, like so. Okay. And this should not surprise you because, for instance, when we studied fermion, right, we tried like, okay, this with the positive frequency or V with the negative frequency. And if this carries a 4-degree freedom, I just put the prefactor, profile function, which carries 4-degree freedom. And since I know there's a vector, Lorentz vector structure, I'm just putting that same thing. And whatever internal degree freedom, this guy will know. Okay, so that's what I'm setting. So if you plug in, what do you get? So from this, you get, let me cancel out the factors of 2 everywhere. If you plug in, what do you get? So p squared epsilon mu, nu. So that's the first term. And then the second term gives you a, b, k nu, sorry, p nu epsilon mu. That's the second term. And then you get c times epsilon nu equal to 0. So this is the equation of motion. So you should view this as basically some operator, which is a 4x4 acting on 4 times 1 column vector, right? Yes.
Sorry, why did you restore a B?
Oh, because I wanted to give you another way of discovering that something like this has to be inversed.
I see.
Okay, so there's a one argument I gave you based on non-perturbative unitary argument, and then here suppose I never heard of that. And let's just proceed and see whether we can rediscover the fact. Okay, just by looking at the equation of the motion.
I see.
Okay, so that's the motivation. Any other question? Yes,
When we use A plus B equals to 0,
yes.
it was P equals to infinity limit. Right? We use P equals to infinity limit.
Yeah.
But then, can we use the same Lagrange? We can measure final motivation and so on.
Good. So I guess if I understood it correctly, the question is, looks like this constraint comes from taking a very high energy limit.
Yeah.
And could it be completely wrong if I nevertheless use it low energy and somehow, cure that high energy? Yeah, that is possible actually. And that actually happened in Santa Monica. Okay. So in fact, Santa Monica has this space where there's some sickness. And then before you hit the problem, it cures the problem. Yes. Otherwise known as Higgs mechanism. But okay. Yeah, I don't know if you see that way. Nevertheless, it happens. Right, coming back to this equation of motion. Let's actually now analyze this equation a little bit. Good. So once again, you should view this equation as something like 4x4 matrix acting on 4-component column vector equal to 0 equation. Okay, so that's how you want to read this equation. Good. So then let's see. So let's try two cases because epsilon mu is nothing but capturing these prefactors. Let's first look at the solution where epsilon mu is proportional to the momentum. So basically, I'm looking at this piece. Is that clear? So here is a general equation of motion. I'm gonna look at this particular sector. Okay, and then we can check this part too. So if I zoom into this sector, the equation of motion becomes A times P squared, and then this will give you another P squared. So basically you get A plus B times P squared, and then plus the C. If I say there is a matrix, which if I call A, so let me just set that to be like so, then times A should equal to 0. Okay, that's the equation. Okay. Good. Now let's explore. So suppose, here, if A plus B were to be 0, first of all, suppose we satisfied somehow accidentally, and somehow we pick the mass parameter you might call is not equal to 0. Then what do you discover here in this case mathematically? So again, this is the equation. And then I somehow set this to be 0. I pick the choice. And then this is not 0. Then you find out that the only possible solution is that this has to be 0, which means that this this is 0. So basically what that means is that the scalar degree freedom projected out, meaning that degree freedom cannot exist. Let's re-understand what I just said. So what that means is as follows. Somehow, if we pick the A and B relation correctly, consistently with the unitarity, and then if I look at, okay, before that, let me say that. So this equation is nothing but Klein-Gordon equation, right? Some P squared times some mass parameter equal to 0. That's Klein-Gordon equation. Okay. So this is Klein-Gordon equation for, if you like, a scalar degree freedom, right? Including the vector, Lorentz vector. And this statement is somehow, if I pick correctly, meaning which I didn't know, and then if I look at the massive theory, then that theory actually doesn't include scalar degree freedom, and secretly it will only include this term. Now, but let's try the other one. Suppose I picked A and B such that this is not equal to 0. You can learn many things. So if you look at the C is not equal to 0, then you have to conclude that some of the solution is in such a way that it should have this mass. Right? Okay. What about the other case? I don't know if this is can capture. What about you again pick this, but you pick c equal to 0? Then what? Then what did you say? So is that what I said? No, I didn't say. Then what happens? Then I guess you have to conclude that p squared is 0. So you can go through that, but at least one thing that I wanted to point it out through this exercise is that if we picked this correctly, which I already explained the why, then we learn one extra information about the physics. In that case, look, this scalar mode is projected out. There's no that mode actually in the theory, even though we keep the entire A mu as a notation for the field. Okay, so then with that, let's next time actually let's look at the now equation for transverse mode, meaning this mode. So continuing, this time let me pick epsilon such that epsilon is proportional to the momentum. I know that this should correspond to this transverse mode or rotational vector. So then the equations of motion becomes a p square epsilon nu, just using this, but that term vanishes because that's how I picked that, and then plus c epsilon nu is equal to 0. So the consistent solution is p square should be c over a. So this should be nothing but the mass parameter for the transverse mode. Right, so this is literally Klein-Gordon equation now. Okay, and this should be interpreted as a mass parameter for the transverse mode. Okay, so that's what we can learn by studying the equations of motion, but we're going to study once again the equations of motion in slightly different form. But before that, questions.
Why didn't you deal with the case where A plus and C equals 0?
Both are 0?
Yeah.
Good. We will, and that's another very most important case too, actually. So let's consider this and the c equal to 0. You might say naively, oh, looks like everything is consistent because this is trivially true. It looks like any A is allowed, right? And in fact, so this case is this is the case that need most care. I mean, this is the subtle case. In fact, that is the massless photon case. And instead of saying there is this projection of the degree of freedom, we will encounter slightly subtler concept like gauge invariance and stuff like that. So yeah, we will study this a lot, basically. Okay. Okay. So let's actually study the equations of motion the second version way. Meaning now I'm gonna just take a look at this case. Okay, by which I mean I already said A plus B is equal to 0 condition. Okay, so I'm consistent with unitary for now, and then let's study that equations of motion. So equations of motion, if you do it, you will find the following. So for instance, you will find that A times. So I have a 2F, and F is roughly speaking derivative of A. Right? So I'm going to have 2 factors of that. So you will find that F nu mu and then from second factor you get also factors of 2 A nu equal to 0. Let's see yes. Okay. So there are 2 factors of F mu nu. So I'm going to take the derivative with respect to one of these 2. There's factors of 2. Oh, there's a factor of 2 missed. And then on top of that, since I'm taking the derivative with respect to derivative of field, I have to take the derivatives. That's what I'm doing. But there's a relative minus sign. But instead of mu nu, I wrote it as a nu mu to take care of that relative minus sign. And then I think I'm missing probable vectors of 2 here. Well, probably not actually. Make sure. Yeah, I think it's not. The reason is, So there are two f's, so that's one factors of two. But then what I'm actually taking derivative is actually derivative of a. But this thing has a two derivative, it's two terms in it, remember, so there are two of them. Okay, so if you take that into account, this is good exercise. In fact, you get factors of 4, and this should be the answer. Okay, so let's study this. Now, this time this should be quick. And one important property of a field strength, as you see from here clearly, field strength is antisymmetric to tensor, right? Because if you flip mu, this is manifestly antisymmetric. So then, if I take a total divergence of this expression, so then the first term is 0. Okay, and then therefore you learn that by consistency, this is always true. Okay, so along the on-shell trajectory, you always satisfy this condition. And this is nothing but your theory only include transverse mode. So that's consistent with what we said here, right? So if I picked a plus b equal to 0 correctly, and if I pick c is not equal to 0, meaning I kept this term, then equations of motion already consistently imposes the condition that I only include transverse mode, not the scalar mode. So what have we discovered? So from now on, I'm gonna take a convention that since I don't know the sign, I'm gonna pick a plus minus and then 1/4 and then half. And then I don't know the sign here. And well, I know the sign here because if you look at this, let me see. No, so for now, say we don't know the sign, then what we learned is that this action, this Lagrangian, even though it is written in terms of a 4 Lorentz vector, this is actually a theory of only 3 degrees of freedom, which is transverse mode. Okay, good. So this theory is called now the name, as you may heard, called the Proca theory. This is called Proca. Probably that's the person who wrote down the first. Okay, there's a relative minus sign. Let me fix that. There's a relative minus sign. Let's fix that. You can fix this. How you can fix here, right? So let me do it again because I was too quick. So let me go back before I actually finish write down this. Let me go back. But what I have done is that there was an A here, and then there was a C here, right? That was what I had. And then this exercise, which is equations of motion for transverse mode, tells me that this is the answer. And then this is the mass parameter for transverse mode. And in order to have a positive mass for the transverse mode, I know that the sign of C should be opposite of that of A. So first of all, there should be relative minus sign. Okay. And then the factors of a 4 and 2 can be picked so that, first of all, you're going to write down for the mass term, you're going to write down half, for instance. Right? Because if you take a derivative, 2 cancels this half. So that's convention. Nice convention. And then if I pick a minus sign here, because that's how you might see it for scalar field. So suppose you fix that way. Then I know it should be the sign of this prefactor should be opposite of that. That's for instance plus. And then instead of half, I put 4, 1/4, because when I was deriving equations of motion, right, there was factors of 4 from derivative of this term versus factors of 2 from the derivative of this term. Okay, so I picked the 4 here. And then since there's overall minus sign that I don't know, I'm gonna include this overall sign issue.
T squared. T squared, there is no mass.
Oh, well, I forgot the parameter. That's what you mean. Was that the question? Okay, so let me keep the mass. So since I know it's mass parameter, I'm gonna write it as m squared. If you're not convinced, what you can do is that suppose you assume now positive number A, and then half of a positive number B minus, the B is confusing, C. Okay, so since at least you know this a relative minus should be there, start out from this. And then just derive the equations of motion, first of all. And then since you know it is a C over A is the mass parameter. If I want to declare that C itself is a mass parameter, I know that this should be a numerical number. Right? Because that already made up entire dimension. This is numerical number. Then the way you can fix is that now if you derive equations of motion, you want to get already just P squared minus M squared acting on the transverse polarization equal to 0, right? That's what you want to see, because this is the Klein-Gordon equation you want to see. So that's how you fix it, is whether 1/4 or 1/2. Okay, so that's how you can fix that. So good. So far what we have learned, we just start writing down the most general action at quadratic in field, and then no more than 2 derivatives. And then by now we basically fixed most of it, other than overall sign, by imposing unitarity and then asking sensible mass term for the photon. And then by studying that, effectively imposing A plus B, actually A plus B equal to 0, successfully projected out a scalar mode. And this theory, even though it looks like written in terms of a full Lorentz vector, actually contains only transverse degree of freedom. So far, that's what we learned. Good. Let's move on. Where is that? Okay. Any questions? Okay, so with that, everything fixed up. Now, equations of motion actually, I already wrote everything. So mu minus m squared a nu equal to 0. So this is the equation. Okay, so everything fixed up the way I said. So then, using the definition of this thing, which is nu a mu minus mu a nu. So if you plug in, you find that this hence the a mu, that's 0, right? So that's the consistency. Remember, now equations of motion is this and this, as we just derived. So there are these conditions we have to keep in mind all the way through. So therefore, first term just vanishes. Second term gives box a nu, and then plus m squared, because there's a relative minus in both of them, meaning there's a minus n in both of them, a nu equal to 0. So indeed, only transverse mode and those 3 degree of freedom satisfies Klein-Gordon equation, as you'd expect. Okay, and that's how we fixed all the coefficients. Okay, good so far. Any questions? Good. So we constructed the theory that describes only the 1,0 R representation without a 0,0 representation. That's what happened. Good. Now, you may recall that, so basically we have done this sort of business for fermion. And back then, there was 2 issues. One was normalization, how to normalize the solution. And then there was the question of completeness relation. I'm going to remind you. So by normalization, I meant in the case of fermion, we had psi goes to u, so p like e to the minus p dot x, and then there was another one for the v, e to the plus I p dot x, and then we discussed how we have to normalize these profile functions. And then the way we fixed the normalization was given 2 spin degree of freedom, we normalized such that this is 2 p mu delta rs. Okay, so that's how we normalized. And then same for the v. We talked about, if you recall, we talked about bilinears. This is the Lorentz vector, and then P is the only vector we wrote down that way. And then using the equations of motion, you can also show that another way of normalizing this state is basically U bar U. And then this time you can show that this should be equal to this. And then similarly for B, but with the minus sign. Because for completeness, B bar B is minus 2f. So that was how we normalize a state or this scalar field. And then there was a completeness relation, or otherwise known as projection operator. So since this guy carried 2 spin degree freedom, summing over 1 and 2, and then we look at the U R P, U bar R. So I'm summing over same spin, but and then P, and then we show that this is equal to P slash plus F. And then if we do the same thing, V bar, we said, okay, that is P minus F. Okay, so we talked about this is the projection onto the particle versus antiparticle sector, and we also talked about the projection onto a helicity part too. Okay, using the gamma phi. So now the question is, okay, so we have constructed a vector theory, and then what will be the statement that is a counterpart of this discussion? Okay, so we have to also fix the normalization, and then we can ask whether there's a projection operator for the vector field. So that's the next discussion. Well, since you learned one thing carefully, next thing can be done relatively quickly. So here is the vector field, and then again, this is how I set up for positive frequency. You can see what about the negative frequency, which is basically complex conjugation of this, because this is a real field. Meaning, by real, I mean there's no separate mode function for complex conjugation, right? This is the same thing. Or if you confuse what I just said, you might tend to say, oh, I want to set up this to be something else, like d nu e to the plus IP dot x. That's like we set up the separate function, but reality condition says that d mu should be equal to epsilon mu star. So this is a reality condition. Okay, there's no separate polarization degree theta. Okay, now let's first talk about normalization. And remembering that this epsilon is always proportional to the p. Okay, so that's the equation from this transversality. So given a time-like vector, so particle is propagating, then I want to pick out a vectors which is orthogonal to that time-like vector, right? So therefore, given a time-like vector, I want to look at the orthogonal space, and then I want to pick out 3 orthogonal vectors, like so. Okay, remember we talked about 4 dimensions, because this is obviously 3D picture. So that means that there's gonna be 3 polarization degree freedom, just like we had a 2 spin degree freedom. And then that means I want to pick out a 3. So this is now space-like vectors, or the mu time-like. Make sense? Okay. So for a given time-like propagating vector, obviously this is space-like because it's orthogonal to that. And then I'm going to pick out the 3 orthogonal or orthonormal vectors. So I want to normalize. So we normalize this this polarization vector in a way that, did I ever wrote down the fact this is polarization vector? If not, here we go. This is polarization vector. And you will see why this text interpretation as a polarization vector pretty soon now, basically now. So we normalize that such that, so if I pick 2 of them, so 2 of them are S star mu. So I just took a product of 2. Okay, just like here, I take a product of 1 U one U star. Okay, I'm doing the same here. So, okay, one epsilon and one epsilon star, and then for two different polarization states, we are normalizing this with one, but one in a sense of delta RS. So that's how we, this is our normalization convention, if you want. Now, this is manifestly Lorentz invariant, right? This is a manifestly Lorentz invariant contraction out of the three Lorentz vectors. So obviously, this condition should be true any frame. Is that clear? So this equation is Lorentz invariant equation, right? So this should be true anywhere. And second, you might say, why minus sign there? Well, I told you, this is a space-like vectors. So if you had a 0 and pi and then 0 ki, so here you go. We have a two space-like vectors. And then if you take inner product of two, what do you get? 0, because it's 0, minus pi ki. So if I have purely space-like vectors, obviously there's a relative minus sign always. So that's why I put the minus sign so that this is consistent with this structure. Okay. Good. So we normalize that way. Now let's understand a little bit more about this physical aspect of it. Questions?
근데 그 파이를 무시하고 하고 있는데 파이가 하모닉 펑션이면은 괜찮잖아요.
Okay, so the question was, we've been dropping this guy. And then, if I understood correctly, if this is harmonic function, by which you mean this?
Yes.
So good. So let's make sure we have not been, we have not disrespected pi. Okay, we've been embracing pi so far, but not us, but unitarily. There's this God-given concept. Unitarily said that I know you're like pi, but pi cannot be part of this party. So. Right? I mean, a mu, I've never been like, I have never written any expression explicitly like so. Right? So I've been writing everything is this. But there's this machine going, and then this machine is designed by a factory with the name unitarity factory. And then that factory produces this guy, but automatically always get rid of this. Now, having said that, if I did not answer your question, please ask him. Good. Good. Any other questions? Okay, so does this all make sense? Okay, so there are three. So let's take some examples of the choice of this polarization vectors. So since we're talking about massive vector field, so we can go for, since p squared is equal to m squared, which is we take it to be non-zero for now, we can go to the rest frame. We can boost, Lorentz boost, everything is Lorentz invariant such that this looks like there's a mass and then zero momentum. In this particular frame, I can choose, epsilon 3 polarization vectors as follows. So let me drop the Lorentz index for now, 0, because I need to write down the space like, and also I cannot do it because there's m, 1, 0, 0. Epsilon 2, 0, 0, 0, 1, epsilon 3, 0, 0, 0, oh, nobody complained. Amazing. Good. So this looks like obvious choice. In fact, this particular choice corresponds to if I abuse language a little bit, even though I'm talking about massive vector field. Suppose I abuse a little bit, imagining that I'm talking about strictly photon electromagnetism. This corresponds to polarization, linear polarization. Okay, so probably I have to explain. What do I mean by abuse already? Because I never mentioned any connection of this theory to E and M yet. So let me first say that, and then let me also explain why this is linear polarization. So here was our theory. One first F mu nu, and F M squared A mu. So we have to be very careful about this term eventually when we take M goes to zero limit. But for now, in case you remember or you took E and M in that way, so this is an antisymmetric two tensor, which means that there's entries filling up the, so basically this guy has entry, which is 0, 0, 0, 0, that's antisymmetric. And then there's a one entry, and then two entry, and then, three entry. And then this should be basically minus of that, right? So there's a 6 component secretly that this tensor captures. And you may remember that from the ENM, okay, you don't even have to remember, let me just write. So this is that, and then nu A mu. So suppose I interpret this A mu as there's a secret, there's a scalar potential and the vector potential. Okay, so let's just study this guy. So first, let's look at the 0, I. So what do I have? 0, I. That's the Lorentz vector. Sorry, the 3D vector, and then I 0. And then, so this looks like what? Time derivative of a vector, minus, okay, actually, minus, do I want to say minus? Minus, okay. Actually, I want to say plus. Guess why? I'll let you figure out why I want to say plus. It looks like this. Okay, so if you happen to remember, this is what you say in ENM electric field. Now let's also look at the IJ. Now IJ, J, I. So this is like there's a vector, and then this is the expression for cross product, right? So this is, if you actually work it out, this is that, and this is what you usually call a magnetic field. So what that means is that if I never look at this term for now, but again, I'm warning you that taking M0 goes limit, zero limit has a subtlety, so we will have to discuss. But for now, let's just forget about that, and then this term secretly captures physics of E and M. Okay. So then when I say linear polarization in this abuse of language here, what do I mean by that? What do I mean is that, so then electric field in this ENM sense, right? There is a 3D vector, which is the direction of a propagation in space and time. Okay, there's a particular vector, like a z direction, and this photon is going that direction. Okay, then perpendicular plane, I have a orthonormal vector that describes the polarization of electric field. So I can write it as, for instance, one basis vector, if you like, and then another basis vector in the e to the minus ip dot x. Okay, so now in this case, if this two polarization vector has the same phase, meaning either both are real or both are imaginary or something like that, meaning in the complex plane sense, they have the same direction. So suppose, example, let's take both polarization vector to be real. Okay, just real, or R2, I don't know, just real. Okay, or R3, anyway, real. So like here, so if you look at the 1, 2, that's literally real. Okay, then the actual electric field you have to take is a real part of this field. That's the actual physics that measures. So that means that this everything is real for now. So that means you have E1 epsilon 1 plus E2 epsilon 2, and the real, which is like cosine k factor x minus omega t. I just expanded out. So there's oscillatory, but then this particular polarization vector always points to the one particular direction, right? Once you specify the size of the E1, E2, and then for fixed basis, this thing is always pointing particular direction, never changes, and only there's this keep going direction, okay? So it's a linear polarization. Good. So now let's take the second example. let's take the second example. Good, so now let's take as a second possible choice, let's take E1 to be 1 of square root 2. Okay, so that's I0. And then as a second basis vector, let me take minus I0, and then third, that's 0, 0, 0, 1. Okay. So now claim is this should describe a circular polarization. Okay, let's check again quickly. So now, according to this definition, this E1, E2 has a different phase, right? Good. So then, good. So then, let's again read off the, real part of the E field here, according to this one. So this thing has a cosine plus I times sine. Okay. So first, let's only look at this piece. So according to the from the E1 piece, let's just look at the E1 piece. What does this give? And okay, so just to simplify, I mean, we can just take arbitrary E1, E2, but let's simplify a little bit because there's no point of making the most general expression. So E is the common size E0, and then E1 plus E2 e to the minus IP x. Okay, good. Well, here you are. So now this thing has E0. So if I take now real part of this guy, what do you get? So this component x direction is real, which means that I have to take a cosine part from here. So that means I have cosine like k dot x minus omega t, and then let me call x direction, like so, okay? And then y direction is either plus or minus I. So let me just keep that in. Either plus minus EY direction, but then since I'm picking up the I factor here, I have to look at the sine part, right? Plus I sine. And up to minus I, we can figure that out. And that will give you sine a dot x minus omega t. Good. So to see why this is a circular polarization, when actually E1, E2 are same here. Otherwise, it's elliptical. So then let's look at the fixed time. So let's just look at the fixed position. So let's look at the x is at origin. Okay, so I'm just look at there's a propagating mode. I'm just looking at the specific position in space, and then this photon is passing through. I'm just looking at reading off the polarization at that point. But let's see what happens. So this is literally 0. This is literally 0. Then you see EX squared plus EY squared is always added to 1. So there is certainly is following this trajectory of radius equal to 1. But then as time changes, phase changes. So for instance, when t equal to 0, it's maximally along the x direction. When this is time equal to 0, right? And then when time equals in such a way that this is pi over 2, it went up to this. So it's rotating that way. And that is the case when this is the positive sign, and it's called positive helicity state. When things rotate that way. If you pick the minus sign, according to this, then it's going to rotate opposite direction, and that's called negative helicity state. So anyway, so here I'm just quickly explaining you that according to this physics, given a time-like polarization, we can pick a 3 basis vector, but different choices basis vector sometimes describe either linear or circular or elliptical polarizations. Okay, good. I want to discuss one last example of choice of this polarization basis, because that will teach us again another some other physics. Question. Good. You are doing good. Hold on. We are doing very good, isn't it? No, I'm doing good. So let's talk about the third example. I mean, in terms of time, So let's talk about the third example. Now, instead of we look at the rest frame, let's look at the general frame. So I'm gonna pick P momentum to be energy, but I want to pick out a particular direction. For instance, 0, 0, and Z direction. But this is without loss of any generality, because any direction of propagation, I can define that to be Z direction. So in this frame, then obviously I can choose this to be the same, 0, 0, epsilon 2, 0, 0, 1, 0. But then, because of that, now the sensible choice of a third polarization is going to be PZ 0, 0, E. So at least you can check that. So up to this point, you can check that P mu epsilon mu third is 0, right? Because in the product is this times minus that, right? However, you also have to make sure that, square of this thing should be -1. Okay, so that's how we decide to normalize polarization vector. So if you just do this, what you get? You get PG squared minus E squared, which is minus M squared. So in order to normalize that to be -1, I need to divide it by 1 over M. Okay, so I'm just gonna put 1 over M to normalize that. Good. So what do I want to say with this? So these are 3 polarization degree of freedom of massive vector field. Okay? Recall, we are still studying 1,0 theory. Right? So I projected out nicely. And there is, so now this thing is propagating along the Z direction, as you can see from this definition, right? This choice. So there is a vector field or if you like, excitation that is propagating along the Z direction. And then these two, epsilon 1 and 2, are orthogonal to that Z direction. But this is actually pointing along the Z direction. If you just look at only the spatial part of it, okay, not including zeroth component. So in that sense, this is really transverse. So now you may remember I said something about it, and this I can say longitudinal polarization. Okay, because it's along the direction of a propagation. Okay, so now I want to note again. Previously, we decomposed this guy into T part and then scalar part. So not incorrectly. So in Coleman, I also said that last time. This can be called longitudinal, and this is transverse, because this satisfies the 4D version of a transversality condition. Okay, now I'm talking about 3D version, sorry, here. Okay, because I already projected at this. I'm only looking at this. This has a 3 degree freedom, and then I'm saying, in the sense of a 3 space sense, this is genuinely transverse. This is along the direction of polarization in 3D sense. So I'm just calling that longitudinal polarization. So I'm stressing out so that you don't get confused that this is not this. Okay, this is one of them. Good. So what I want to say is that suppose now I had this theory, meaning I have this massive vector field, and then suppose I couple that to some matter field. Okay, which we will discuss consistent coupling next time more carefully. There's a nice story there. But for now, let's couple. So let's add interaction Lagrangian on top of what we had in the following form. So if you want, let's talk about the fermion, how to couple the fermion to the vector. And you should know the answer. Why? Since I'm going to couple that to some vector. And then the question is, can I construct a Lorentz vector out of the fermion? So we talked about all 16 bilinears, right? So we had a scalar, pseudoscalar vector, pseudovector tensor. We talked about all of that. So you should say, oh, that's just piece of cake. Okay, that. If there was a vector, good. So we know how to add an interaction term. Okay, good. You can also do similar thing with a scalar too, because given a scalar, you should be able to construct the vector two. Basically, phi dagger nu phi plus some Hermitian conjugate. Basically. Okay, so up to vectors of I. But anyway, you know what to do. Suppose we have add that. Suppose we have add that. Then I can ask the following question. Suppose we added both. Okay, so you see the way matter field, other field like scalar fermion, coupled to this vector field is through this bilinears. Okay, at least at this minimal level. Again, next time I'm gonna derive more conceptually why this is a good choice to do. But for now, let's assume that. So then I can ask the following scattering process. Suppose I shoot in, two scalar, and then well, I can just do this. So let me just use the fermion. I can use a fermion coming in, and then this vector field comes out. So this is my notation for fermion, and this is my notation for vector field. Okay, so we will eventually, this is one of the diagrams you will see eventually QED when we establish massless limit carefully. But anyway, for now, let's just study this. Okay, so now you can ask the following question. As an experimentalist, I'm going to have a detector. And then I'm just asking, I want to look at the particular polarization mode. Last time, when we talked about the fermion, so we talked about the following, if you remember. So there's a blah, and then, I don't know, all kinds of stuff coming in and all kinds of stuff coming out. And so then, first we said, oh, beam, usually we use unpolarized beam, so we have the average over spin. And the detector, since usually we cannot probe particular spin state, we are going to have to sum over all spins, right? So we have done that last time. Here, just ideally, let's imagine that nevertheless, I can probe a spin state of this vector field. And then suppose we ask the following question, as an experimentalist, I'm going to actually probe only the longitudinal polarization mode. Okay, I can ask the question physically. So then what would happen? What would happen is that just like if we had a fermion, you had this going against the charge flow, you had a U bar U, for instance, right? There's this polarization vector as a part of the Feynman rules. Just like so, eventually, when we talk about Feynman rules, for external vector field, we will have a polarization vector here and there. Okay, so then what you're going to have is that your amplitude or cross section will have some part of the some gauge coupling, so G square, naively, and then two longitudinal polarization vectors. Okay, so for instance, I will have two polarization vectors, and this is amplitude. Maybe you have to square to get the cross section. Okay, now let's take the high energy limit. Suppose I go to the energy region where energy is much greater than mass of the vector field. Okay, so I'm running this collider so that the energy is way bigger than the mass of the vector field, which I can do. Then what happens? In this limit, polarization vector for the longitudinal mode, which is my third polarization vector, goes like, because at high energy regime, momentum is of the same size of energy. Like as if I'm doing the massless limit, right? That means that polarization vector becomes E over M. So I can pull out the E over M. So then this thing will have something schematically, naively, E over M to the power. In this case, probably square, probably something subtle happens. But anyway, super naively, you expect something like this. Okay, although there's a subtlety, but let me be naive. So far, so good? Are you with me so far? And then what happens? Is this all good? I just computed, honestly, as we'll learn about the perturbation theory, right? Suppose we have done the calculation. Then what would happen? As energy keeps growing, with the fixed mass, looks like this can grow indefinitely. So cross section of a producing longitudinal mode looks like can grow like indefinitely. So if I use a more and more energetic collider, it looks like this can go more and more. The question is whether that makes sense or not. Recall, cross section, which has a dimension in it, but nevertheless is a measure of a probability to produce such a process to happen. Therefore, there should be an upper bound in a proper sense that this cross section cannot grow more than something, right? I say more than something instead of saying more than one, because once again, this is a dimensional quantity. Nevertheless, this is sort of computing probability for a given process to happen. So what we learned is that if I hide a massive vector field, and then if I couple that to some matter field, so that I can ask this sort of dynamical question, this longitudinal mode sector signals the fact that this theory at some point should break down, because looks like this, this probability grows indefinitely. So at some point you will, in a sense, lose the notion of unitarity. Like if you start out with some fixed probability, you expect that unitarity says that probability should be preserved, right? But if this grows indefinitely as you go to the higher and higher energy, how come unitarity still works? So this is called the unitarity problem, for instance. Slightly more sharply, let me say it. I don't know if that's going to make sense to you, but let me say it. So when this phenomena happens, in other words, you compute something in perturbation theory, and then, for instance, you look at some asymptotic behavior, and then you found out that something is not right? Because in this case, probability goes to shoot up. Then this signals either what's known as a unitary breaks down, because notion of probability breaks down, or perturbation theory breaks down. Does that make sense? Because how we have computed this, assuming perturbation theory works, I computed this cross section, and then probability goes outside of the regime that I'm happy. So either unitary breaks down or perturbation theory breaks down. So this problem, if that happens, for instance, can be cured either way. Either you say, oh, I want to stay in the perturbation theory. What that means is that we're going to stay in this recoupling regime. But then unitarity has to be restored. And often that happens all of a sudden at some high energy scale, some new degree of freedom appears. And then they cancels out against this blowing behavior. So two solutions, still weakly couple the field theory, but unitarity is restored by having extra new particle appearing at high energy, so canceling out this behavior. Okay, that's what happened in standard model. Second solution is that no, I believe still quantum mechanics is working, which means that you have to give up on perturbativity, which means that at some high energy scale, theory becomes strongly coupled, and then there's a super strongly coupled sector appearing. Okay, so this is versus what happens in QCD. Okay, so there's this pion, nice perturbative field. They compute the cross section. It grows. Again, either unitary breaks down or perturbative theory breaks down. There, what happened in QCD is that things become strongly coupled, and then new world open for a single one. Anyway, so that's another thing that I wanted to keep pointed out. It's interesting physics to know. Okay. Good. That's it. So next, I want to derive a completeness relation. So far, I talked about normalization of polarization vectors, and then I just talked about three possible choices in each of the physics meaning: linear, circular, and then this particular interesting physics problem. Yes.
So if two outgoing one have same coordination vector,
Yeah.
does that mean the final state we have spin two states?
Okay, good. So that will depend on, so first of all, total angular momentum here should be the same as the total angular momentum here, right? So that'll depend on what is the exact configuration. Starting from, for instance, here, let me just write this way. Either you start out with a half zero, or 0.5, and then you can ask what are the possible spin sum. Okay, so expect if your initial Fermion state were like this eigenstate of the angular momentum, then possible spin sum is only half and half. So somehow then this should be spin one state, for instance. On the other hand, let's see if that's possible. If it were something else, like a half have some other particle in such a way that if the initial state happened to be spin 2 possible, or spin 2, which I don't see for this particular process, then possibly final state has to be spin 2 state. But what I'm saying is that whatever it happens, angular momentum preserves, and you can answer that by looking at, for instance, what was the total spin of the total angular momentum of the initial state.
For this case, the maximum spin of the initial state is.
I think it's 1.
Yeah, I wonder why we can have same largest vector only the.
Oh, that's your question. So the question I believe is like, if this is the case, then whether these two can be the same.
Yeah.
Okay, probably, okay, here I was being a little bit naive. I don't know if we actually factor that in carefully, because I was thinking naively actually, closing up and then this, so that everything is possible. But then if I look at this, yes, good question. Maybe one of these may need to be transverse mode. Maybe this transverse mode. And this is like scalar, this is spin 1. Maybe that's how it works.
The cross section will be different.
But yeah, but nevertheless, still there's a 1 factor of epsilon L. Whenever you have epsilon L, there's always blowing up behavior. But it may be blowing up less. Good. Now let's talk about completeness relation. By the way, this was the key observation back in the day, 1980. Okay, so in the standard model, we knew there are massive vector boson called the Z and the W. And then people computed cross section of like longitudinal, some block, longitudinal W goes to W. And then they panicked. Like something like this happened. Okay, and then there is what's known as a Freud-Stark bound, which is basically like absolute upper bound on the cross section has to satisfy if it ever can be unitary. Okay, just like we talked about some non-perturbative unitarity, there is a similar statement for the 2-to-2 scattering process. There's an absolute upper bound, a non-perturbative upper bound that the cross section has to satisfy. So they found that this can easily shoot up. Okay, and the same question. Oh, what's going to happen? Either unitarity should be restored by new particle appearing at some scale, or we have to give up on recoupling calculation, meaning there's a strong dynamics should show up. Okay, there was beautiful time in particle physics. Back then we were the king. Okay, nobody can. Why? We had almost a mathematical theorem that new physics will appear, as you see from this argument. So we know if you give me collider, I can give you Nobel Prize 100%. Because we know something is going to happen. It was good time. And standard model, the way it was fixed is not turning this into the strong dynamics, but actually all of a sudden, so cyclically there was a W boson, and then there was a Higgs appeared. And then this canceled against that, and then unitary restored. Beautiful. Good time has gone, but yes.
It's gone.
No, only that piece of good time has gone. You might say, wow, then what should we do about the particle physics? But then we have to ask it backward. Okay, hopefully this, yeah, I don't mind. The way science works is not we promising to the community that we have a mathematical theorem level of statement for new physics. Then I don't need to convince, or I don't need to, persuade. Okay, I just say, give me money, right? Because I have a mathematical statement. Why should I be like, can you please? I don't have to do that. But most of the science, the way it works is that, wow, I don't know what's out there. Let's just look out and let's shoot out the very expensive telescope, see what happens there, right? And then, wow, there's nice pictures, and oh, we saw more galaxies and we saw more stuff. See, cool, that's enough. But particle high energy theory, we've been playing so well that we went into the level that we can even convince the community at the mathematical level. But I want to just make sure that this is not how science progresses. We're just curious, we just look at and see what happens usually. Anyway, let's go. So overall, high energy is doing good. And we expect a lot of fun to happen. All right, so let's now talk about a completeness relation. Okay, so once again, I want to get something like UU bar is P slash plus M, that kind of expression. Okay, so it's clear setup. So let's define a projection or some operator, which is product of epsilon mu, epsilon nu, R star. And then R goes 1 to 3, because I have a 3 degree freedom. Okay, so how do we fix this thing? First of all, without even doing anything, so this is 2 tensor. In fact, this is a symmetric 2 tensor, right? There's nothing stops me from doing this. This is bosonic field function object, right? So that I know that there are, so then I can ask, how can I construct a symmetric 2 tensor? I have a 2 object. First of all, recall this is a function of momentum. So I have a 2 object to construct a symmetric 2 tensor. One is the metric. So let me just write it as a G. I don't know. Probably I'm mixing up G and eta, depending on how I feel. So today I feel like this. And then the second possibility is I just use the momentum to construct a symmetric 2 tensor like so. So my job is to fix A and B. So let's do it. So first of all, since epsilon mu is perpendicular to the P mu, what that means is that if I take this and then look at the P mu, first of all, because of this piece, if I multiply P mu, that's 0. So this is 0. But the right-hand side says that I have A times P nu, and then this is plus B P square P nu equal to 0. So that's what I get. What that means is that A should be minus, where P squared is M squared times B. Okay, good. So I fixed partially. There's one relationship. Let's take the second. The second is I know that I normalized epsilon mu R epsilon S star mu. So this was the normalization I did. And we fixed that to be delta RS with the important minus sign. So let's just apply this. So I take this guy, P mu nu, and then I multiply S star nu. Oh, actually, let me just actually just this without a star, because I already have a star here. Okay. So if I do that, since I'm multiplying this guy with epsilon s with Lorentz contraction, that gives me minus delta. So I get minus epsilon s from mu. Okay, so that's one side of it. Let's look at the other side of it. The other side says I have A, which is, okay, A, what do I get? If I multiply, well, epsilon s mu, and then B, which is 0, right? Because by the transversality. So I know therefore that A, which is equal to minus M squared B, should be minus 1. So this completely fixes. Therefore, I learned that there's this completeness relation, epsilon mu R, epsilon nu R star should be equal to minus metric. And then B should be what? Oh, sorry, I heard something. I'm sorry?
M squared G. Oh,
Yes. Good. So this is completeness relation, but just like we did last time, you should also view this as a projection operator. Is that clear? And that is clear because by construction, how did we construct this? So basically in 4 dimensions, we factorize the 4-dimensional spacetime into 2 directions. One along the propagation, and second along the perpendicular orthogonal space. Right? Remember, epsilon is literally 3 vector that is perpendicular to the propagation of the propagation. So then from this property, if I had a vector that pointing along the propagation direction, then it projects out. On the other hand, if I take a vector which is orthogonal to that, then it just goes back to up to minus sign. So in that sense, excuse me, this is a completeness relation, but at the same time, this is a projection vector or projection operator onto the transverse 3D space. Is that clear? Good. Okay, so now we are gonna talk about what? Quantization. What questions so far? Okay, good. So let's see. Now, next thing is I was gonna talk about the quantization. I guess I can talk about like 10 minutes, or I can stop here. It's up to you. So,
He needs to go.
I'm sorry.
He needs to go other class.
Sorry.
He needs to go other.
Oh, sorry. Okay, so then why don't we stop here today? And next time we start the quantization and hopefully finish. And then we'll talk about how to couple this theory to matter in a consistent way. We're going to talk about massless limit. We'll talk about gauge invariance and so on. Okay, so that's it. So let's stop here. Thanks. Yeah.
완전 4시에 하셔도 괜찮아요.
But we have 8 minutes, so you can ask.